Hello! In this video we're going to discuss the discovery of the nucleus by Ernest Rutherford, who's the man you can see pictured here. In 1911 he did a really famous and very important experiment which revealed the structure of the atom, and something which really wasn't known beforehand. Okay, so atoms. Here are some numbers to do with atoms, and I've left them as whole numbers rather than standard form just to give you an idea of how many atoms there are in various common things. So an atom is about a tenth of a nanometer in diameter, which is pretty small. And you can see how many there are in you and in the coins that you carry around in your pocket and in everything else around us. If you hold up two fingers, the width of those two fingers together compared to the Earth is about the same as the number of atoms across those two fingers. So if you think about the number of atoms in those two fingers, that's the same as the number of fingers that would stretch across the Earth. So that gives you a bit of an idea how big they are. In terms of the history of the atom, the first people to talk about atoms were the Greeks, and Democritus in ancient Greek coined the term atomos or atomos, which means indivisible or uncuttable, because that's what they thought atoms were. They thought they were the basic building blocks of everything around us, which is true to a certain extent. And because it was such a sort of common sense idea, that stood for thousands of years. And even in the 17th, 18th and 19th centuries, John Dalton, the chemist, thought of matter as little billiard balls, little hard, indivisible pieces of stuff called atoms. And it wasn't until about 1895 when an Englishman, J.J. Thomson, discovered the electron and realised that electrons were negatively charged particles which were in atoms. And that was the first time that people had realised that the atom wasn't the smallest particle, the smallest element of things. Now, when the electron was discovered, the model that was drawn up then was called the Plum pudding model, and we'll have a look at that in a little bit of detail. And that stood only for 10 or 15 years until Rutherford came along. And Rutherford's experiment is the one that we're going to look at here. Rutherford discovered the nucleus. Rutherford did a lot of work on radioactivity and particle physics. In fact, he's sometimes called the father of particle physics because he discovered the proton and various other things, and alpha, beta and gamma radiation, things like that. Then the neutron was discovered in the 20s, 30s, and Niels Bohr and a lot of others then developed the theory of quantum mechanics, which is the best theory of the atom and the subatomic particles that we have today. So let's have a look at of that. Okay, so before Rutherford came along, but after the electron was discovered, this was the model that they had of the atom. And it was called the Plum pudding model because they knew about these little electrons, but they didn't know how they were distributed within the atom, and they didn't know what made up the positive charge, because they knew the atom was neutral overall, and it had negatively charged electrons, which they thought were evenly spread within the atom, and therefore there must have been some sort of sphere of positive charge. And it's a bit like a Christmas pudding, where the electrons are the plums, and the positive charge makes up the rest of the pudding. Which is why it was called the Plum pudding model. And Rutherford set out to test this model to see if it had any validity and to try and explore the atom a little bit more. So what Rutherford did was he got a source of alpha particles. Now they knew that alpha particles were positively charged, and they knew they were quite big. They didn't really know what they were, but they played around with them in magnetic fields and things like that and realised that they were positively charged. And he fired a beam of these particles towards a piece of very thin gold foil, just the sort of same sort of thing as you see in a gold leaf electroscope, that sort of thing. But he'd got one of his students to hammer this foil, literally by hand, as thin as this guy could make it, and he managed to hammer it to within about a 3,000th of an inch thickness, and that's only a few hundred atoms thick. So it was very, very thin, and it was the best way to test this theory with these alpha particles. They knew that gold was very dense, very heavy, the atoms were very, very large, and so that's what they did. And around it, I mean, this is a schematic here, I'll show you the actual apparatus in a minute. there was a fluorescent screen that they were able to rotate around the gold foil. And effectively what happened is the alpha particles hit the gold foil, and then they were scattered through various angles. And Rutherford was trying to measure the scattering angle to see if he could figure out what the structure of the atom was. Here's a picture of the actual apparatus itself. This is an old photograph here, and effectively it was a metal cylinder with a vacuum pipe that came off the bottom here, and all the air would have been pumped out there. And it needed to be done in a vacuum because otherwise the alpha particles would have hit the molecules of the air in the chamber. So if we look at this schematic over here, this here, number 1 and number 2, this is the source of the alpha particles. This was where they were actually produced. This little tube here is a collimator, which made sure that the alpha particles came out all in the same direction. Number 3 is the gold foil. Number 4 over here, this is the actual fluorescent screen. Sorry, I'll keep bringing up my right-click menu. This is the fluorescent screen, which was on the front of this telescopic microscope here. And what they did was they actually looked down this tube in a completely darkened room and counted little flashes from where the alpha particles were hitting the fluorescent screen on the front of the microscope. And then obviously this thing could be rotated all the way around so that they could view this gold foil from different directions. And all they were looking at were tiny little flashes. So, you know, it was quite a difficult experiment to do in terms of, you know, seeing these little things in the dark. Okay, so that's how it worked. Now, what he expected to happen if the plum pudding model was correct was that there'd be effectively no deviation at all. Some of the alpha particles may be deflected by a few degrees as they came into contact with the electrons, but effectively they all would have gone straight through. But that's not what he found at all. What he found was that most of them did go straight through. You know, the great majority were completely undeflected, but there were some, quite a lot actually, that were deflected by quite large angles. And you can see here that that's because they came within quite a close proximity of the nucleus, as we now know, and were repelled by the nucleus, which is the positive charge, and ended up at various points around the detector at various angles. The occasional one, and we're only talking about 1 in 10,000, was actually what we call backscattered. So it approached the nucleus head on and was repelled in the opposite direction. And this was completely unexpected, and Rutherford said at the time it was like firing a 15-inch shell, like a tank shell, at a piece of tissue paper and having it bounce right back at you, because he knew that the alpha particles were heavy and fast and quite penetrating, and yet this gold foil was extremely thin, and so it was a very, very unexpected discovery and result. And it actually took Rutherford himself 2 years to figure out what was going on because the results were so groundbreaking. And there's a very good simulation online, which is one of the PhET simulations, which I'll show you now. And this is the plum pudding model, and these little grey and red balls are the alpha particles. And that shows you what would happen if the plum pudding model were correct. This red blob at the back here is the atom, and the blue dots are the electrons. So no deflection whatsoever. But with the new atom, which is now called the Rutherford atom, or the nuclear atom, this is what happens. Now, this is a much smaller, much tighter scale here. We're talking about nuclear scales. So this is the gold nucleus, just one of the gold nuclei, and you can see the alpha particles bending away from it as they approach. So they're not actually hitting the nucleus, they're being repelled electrostatically, because obviously the alpha particles are positive, and the nucleus is highly positive. The gold nucleus has got 79 protons in it, so its electric field is very large. And so the alpha particles were being repelled. And you can see that the closer they got, the more they were repelled. And the ones that came up right in line with the nucleus were the ones that were backscattered. Obviously, on this scale, you can't see the ones that missed the nucleus completely. So this is just the few that were actually, had gone through large scattering angles rather than the ones that had all gone straight on. There are many hundreds of those for each one of these you can see here. So that's quite a good simulation, and thanks to PhET for making that. Okay, so what did this actually mean? Okay, so they realized that all of the atom's positive charge is contained in this tiny little dot in the middle of the atom. And And almost all of the atom's mass is concentrated in the same place, in this nucleus. So the mass of the nucleus is much larger than the mass of the electrons, and so it makes up almost all of the atom's mass. One of the most surprising things is the size of the nucleus. It's only about 1/10,000th the size of the atom. It's extremely small indeed, and this was probably the most unexpected thing of all. It's incredibly dense and incredibly small. In fact, because it's only 1/10,000th the size of the atom, it means that effectively that 99.99% of all atoms are effectively empty space. There's nothing there at all. And you and I are made of atoms, so 99.99% of everything, including us, is empty. And there's this enormous gulf between the electron shells, and then zooming in right down into the nucleus. You have to go down by 4 powers of 10 in order to get to the nucleus. Okay, so this is the new model of the atom after Rutherford. Notice that we don't have any protons or neutrons yet. All we've discovered is that there's a nucleus in the center. And we also don't know about electron shells yet. So the electrons are still somewhere evenly spread in the nucleus, within the atom. But now we know that the positive charge is concentrated in the center. And what Rutherford discovered is that the radius of the atom is about 10 to the minus 10 meters, as I said, about 0.1 nanometers. But the nucleus is about 10 to the minus 14 meters. So that's, as I say, about 10,000 times smaller. Okay, thank you very much.